When your AI agent runs slowly, you might think that the solution is a better GPU. But new Intel and Nvidia research show that in a lot of agentic workloads, the CPU is becoming the real bottleneck. I want to explain what this news means to you in this video and show you a real example so that you stay ahead of this trend. A lot of people claim that every small development in the AI industry changes everything, but this one actually might do that. I first learned about this phenomenon reading this article on agentic AI demands more than GPUs, and no need to worry, we're not going to read this entire article together. I'm going to give you the key takeaways right now based on these two figures. These two figures neatly represent how the computational need for AI systems like ChatGPT have changed over time. Let's go back in time to when ChatGPT was first released in 2022. What did the inference of ChatGPT look like back then? Well, back then, what you would do is you would take the input of a user, you would have to tokenize it for certain tasks, for example, for RAG, to inject some kind of information into the system prompt relevant for a request. And all of this would be CPU bound, but the actual inference, the part that's running the actual AI model, is all working on the GPU. You have to generate, the GPU has to parse the entire context window of the AI conversation, and of course, generate the output. Nowadays, though, the story has changed a little bit. We don't have this single pass inference model anymore. Let's, for example, take Claude Code. With a use case like Claude Code, you might still have a little bit of tokenization on the CPU side. And of course, you still have the GPU, which is taking in the context window, including all of your code, and then giving a response to your question. However, things are getting more complex now, because next is agent inference, we are orchestrating a bunch of tool calls. Tool calls in Claude Code might include things like web search, which executes a web API, some browser usage, which might execute a pretty heavy Playwright session, or even, of course, running code to validate things like running tests, which might rely on Python code that's also running on the CPU. In this particular example, you can see here how certain tools might connect to a database, which of course is then dependent on the database coming back with an answer. Some of the operations might run on a cloud-based API, or a dedicated machine learning or deep learning model that can actually run on the CPU side, because not every AI model needs to run on a GPU, right? It's usually the case for large language models, but there are plenty of models that can run just fine on the CPU. And even in the case of an API or a database, maybe it's not actually running that on your local CPU, but if you're connecting to, say, a PostgreSQL database, well, that's of course hosted on the server that's running on CPU. So the point here is that we have way more dependencies in this agentic workflow that rely on CPU operations. And a lot of this is really nice theory, but what does this look like in practice? Well, I created a demo that shows just that. So let's head right into that demo. To demonstrate that CPU usage can be very common with tools like Claude Code, I created a demonstration that relies on hooks. If you're not familiar with hooks, hooks are really nice ways to, well, hook into events of an agentic system like Claude Code. For example, I've got a hook here for the session start, which is of course when you spawn a new Claude Code session. And this hook calls Python 3 and it calls this track.py file, which I have over here. And this Python file can basically handle different hook types. It's just a very simple one-off demonstration, so it's not very fancy code. It's just an if-else statement here where we look at the different kind of events and then we record what kind of event took place together with, for example, the type of tool that was called. So we have a hook for session start, a hook before a tool is used, a hook after a tool is used, and a hook when the session ends. And the reason why we have these four hooks is because with all these four hooks, we can basically keep track of whenever a tool is being used and when that tool is actually done. And we can then, of course, measure how long it took for that tool call to resolve. While the simulation is running, let me talk you through a very interesting fact. When we're talking about training AI models, we're talking about a ratio of the industry needing one CPU for every 8 GPUs. Now, this is because some AI models can be trained on a CPU. Sometimes a large language model needs to be trained completely on a GPU, but the CPU can still be used for a lot of data pre-processing. So that's where this ratio comes from. But when it comes to inference, oh, the battery's running out of my lighting. But when it comes to the inference of AI models, the ratio is more like one CPU for every 4 GPUs. Some sources claim, especially on the CPU manufacturer side, that it's closer to 1-to-1. I don't know if I would agree with that in my daily use of AI when it comes to agentic coding, but there's certainly use cases where that's probably the case. In any case, you can see here that CPUs are just becoming more important in the AI infrastructure. And while we're seeing a GPU shortage already, the same is going to apply for CPUs as well. And in fact, manufacturers like Nvidia are now starting to ship state-of-the-art GPU modules with better CPU modules as a sidecar module to help out with this distribution, this need for both GPU and CPU power. Because in general, we have a compute not because in general, we seem to have a compute shortage, and that is not just on the GPU side. Anyway, let's head back to the code and see what the result of the simulation looks like. In addition, we can also measure the amount of idle time between two tool calls, which can represent the amount of GPU time that's being used in Claude Code, but not necessarily, because if I don't type anything into Claude Code, then there will be a lot of time between tool calls, right? So to illustrate that, if I run this example here, UV run simulate, the moment that I press enter, it will actually go ahead and run a bit of code. Now I'm going to approve this command. And once it runs simulate.py, you will actually see that in the background, my CPU is starting to do quite a lot of work. If I check out my CPU usage here, you can see Python 3 is using up a full core. So that seems to work just as intended. Now, it's doing a lot of complicated mathematical calculations here, just to kind of pretend like it's doing a bunch of work that takes a lot of time, like maybe it's calling some kind of machine learning module. And now when it's done, I can actually quit out of the Claude Code session, and then you will see that I get a JSON run here, which represents the events that we have so far. We also, of course, have a simple report. But of course, in this case, you can see that this doesn't make any sense. I've just been idling a lot on the GPU side because I was explaining all of this to you, right? So what instead we want to do is we want to run a simple script, this run script, and this run script will start Claude Code immediately using the P flag to then launch Claude Code and immediately execute the Python script. So we're going to go ahead and run that. And there we go. Now, even this is not very academic because we don't really see the amount of time that's truly spent on GPU calculations. Some of the time we spend here is also spent on sending a request to Claude servers and then actually allocating our requests to certain GPUs in the background. All of this is just to illustrate that CPU is becoming more important with these agentic workflows. This is not meant to be like a real rigorous test. In any case, now it's launching Claude Code and it's running UV run simulate again. And to prove that, we can check out our CPU usage. You can see Python 3 is up here again, using up an entire core. In this specific test, you see that the CPU usage is way more in terms of the amount of time taken than the GPU usage. But I will say this is a little bit of a bar to trick, because if we look at the simulate Python file, you will see that it just creates a fixed duration of 20 seconds of heavy work. The whole point here is just that this is possible. It is possible to have an agentic loop where your CPU usage is much heavier. But just because you spend more time using a CPU doesn't necessarily mean that that time was more expensive. Let me explain what I mean by that. What you saw before was that the script used one of my CPU cores on my Mac, but my Mac has 10 CPU cores, and one CPU core is generally easier to come by compared to a bunch of GPU power. So what I can also do is I can run this exact same script, but then using the multi-core flag. And now you will see that if I check out my CPU usage, that we get multiple Python processes that are using 100% of a single CPU core. And we're actually hitting a much higher peak of my total usage compared to when we ran those other tests. So now let's wait until it's done and see what we get as an end result. While this is running, I wanted to let you know that I create these kinds of demonstrations really quickly using my agentic engineering configuration that you can fetch completely for free in the link in the description down below. So definitely check it out if you want to get the most out of your Claude Code or other agentic coding tool. So now if we check out that new run, we get a pretty similar result because, of course, we're spending almost the exact amount of time on those tool calls, but I was actually using more of my CPU. So the point here is just that measuring CPU versus GPU utilization is not as simple as just looking at the amount of time spent on each of these different pieces of hardware. Because even if you have a one-to-one split between CPU and GPU usage, well, your CPU might be way cheaper than your GPU, right? To be completely honest, you can run most Python code just fine, even on a much older CPU, but you literally cannot run a large language model on a GPU that's, say, 8+ years old. Well, you can try, but it's not going to end very well. So I think that it's just important here to realize that the shift here is definitely real. We are seeing that agentic workflows can take up more CPU time, but you do have to consider what your use case is. There's still plenty of cases where using something like Claude Code with max thinking mode will lead to you waiting much more on the GPU side, because when it comes to running the Python validation, it's probably done in a couple of seconds, whereas it might take a couple of minutes to think about the problem using a GPU. However, if you're using deep research mode in Claude Desktop, maybe the distribution is already a bit different, because Claude Desktop might pull hundreds of web articles to then be researched and processed by the LLM. I still think that in most cases in the real world, GPU utilization is still way more important than CPU, but you can see with articles and research like this that CPUs play an integral role in the AI space. And to be honest, I was a little bit naive about this. I didn't really realize that. So I hope that together with me, you learned something today. And if you want to pick up on these kinds of projects for yourself, to learn more about real AI engineering, again, go and check out my agentic config in the description down below. It's free to fetch, and it will make sure that you get the most out of your agentic coding tools to build demonstrations like this for yourself.